So in this video, I want to talk about the microeconomic tools that are extremely helpful in understanding the proofs in optimal tax theory. So let's go through them as we will need them later on. First thing I want to explain is Shepard's lemma. So what does it say? Well, assume we differentiate the expenditure function with respect to the price of good I. Then what Shepard's lemma says is, well, that yields the demand of good I. So to understand what this is about, we first have to understand the concept of the expenditure function. So the expenditure function tells you how much money you need to afford a certain level of utility given a certain price vector. And what you would expect holds actually true. So the higher the utility level, the more expenditures it takes. And the higher the price level, the more expenditure it takes. So the expenditure function is a function of prices and utility, and usually both parts enter positively. So the expenditure function can be defined as the minimum expenditures that are needed to reach a certain utility level U, given the price vector P. So this concept in mind, we can derive Shepard's lemma. So assume that X star is the consumption bundle that is actually doing the job. It actually minimizes the expenditures given a certain price vector P star and a certain utility level U. Now, if X star is optimal, that is expenditure minimizing, given a certain price vector P star, for some other price vector P prime, well, usually a different consumption bundle will do the job of minimizing expenditures. So for this other price vector P prime, usually X prime will be at least as good as X star, simply because I can re-optimize. Well, in math terms, this means that the expenditure that are minimized given the price vector P prime cannot be higher than, say, stubbornly buying X star, although we are not faced with P star anymore necessarily, but the price vector can depart and can be denoted by P prime. Now, there is one special case, namely if P prime happens to be the same as P star, then, well, X star is expenditure minimizing. That was what we had by definition on the last slide. And then the equality holds. So usually the left-hand side is smaller than the right-hand side, but with P prime equal P star, equality is holding. So that means that the difference here, if we define that as a function which consists out of the difference of the left-hand side and the right-hand side of the inequality, then this difference function has a maximum at P prime equals P star. So this function is usually negative. The highest value it can have is 0, and that happens here. So if this function is differentiable, which happens to be the case if the expenditure function is differentiable, then at this point, we must have that the first order condition holds. So a small change in a price, Pi, therefore must not change G, the difference. Or in math terms, the partial of G with respect to PI is equal to the partial of the expenditure function with respect to PI, that is the partial of this year, minus the partial of this year, and this is simply xi star. And because it's a first order condition, it has to add up to 0. Or we can rewrite that saying that, well, the partial or the differentiation of the expenditure function with respect to the price PI is nothing else than the amount of xi purchased initially. So to give some intuition for Shepard's lemma, I'll give you a simple example. So assume that over the year you are consuming 100 liters of gasoline per year, say. And then the gasoline price increases by 1 cent. Okay, so if you want to continue to buy the 100 liters, you needed €1 more, and then you could purchase the same consumption bundle. So this could be the additional expenditures that you need to keep your utility level. But then you could think twice and say, well, I could adjust to the different price structure, and instead of driving to university by car, I could use the public transport more often. So maybe by reorganizing myself, I can attain the same utility by getting less than the €1. And what Shepard's lemma actually says is, well, that if it's really a marginal price change, then the €1, that is the response in expenditures that you get if you do not react with your expenditure structure, is exactly the right amount. And that's a surprising result maybe, but it makes life very simple to evaluate price changes. The money amount that you need as a compensation for a small price change can be expressed very easily by looking at the amount of the good whose price has changed, period. The next concept in our tour through the microeconomic toolbox is the Sutsky equation. It shows that the effect of a marginal price change can be decomposed into a substitution effect and an income effect. So there are two demand functions that need to be held apart. The Marshallian demand simply plots prices and demand, keeping income fixed. So that is normally what is happening. The price goes up, but nobody cares and nobody gives me additional money so that I get compensated. But then this is exactly what happens with compensated demand. It's calculated under the counterfactual. Rarely is something like that exists, that under the counterfactual that along with the price change, there's an income change such that I am capped on my old indifference curve. I'm capped on my old utility level. So to derive the Slutsky equation, let's simply assume that we have a demand at utility U, and that is a compensated demand. So we denote it as HI as a function of the price level and the utility level. And then the Marshallian demand is a demand that is depending on P, on the price vector, and on the income level. So that's Marshallian demand. And now we can appropriately choose U and Y in such a way that, well, these two demands are equal or identical. So here we have set the Hickshian or compensated demand equal to the Marshallian demand. And how do we do that? Well, we choose Y in such a way that it's just enough to afford the utility level U that we have in the compensated demand. And well, how can we do that? Well, we take the concept of the expenditure function, which is the money amount necessary to afford U. So that is equated here, and this does the trick. And the next step is quite simple. The only thing that we have to do is to differentiate this equation here with respect to the price of some good J. So on the left-hand side, we get the partial of the compensated demand for good I when the price of good J marginally changes. And here on the right-hand side, we get two effects. So if Pj changes, so some element of this vector P changes, that's the first effect. And then also some element of this vector changes, so there's an indirect effect. The change of Pj in here affects the value of the expenditure function, and the value of the expenditure function has an impact on Walrasian demand. So here are the two effects. This is the first effect that comes from taking the partial with respect to the Pj that's included in this vector. And this here is the indirect effect. So we have here the inner derivative, the partial of E with respect to Pj, and we multiply it by the outer derivative, that is the marginal effect that E has on D. In the next step, we just rearrange that, solving on the left-hand side for the partial of the Walrasian demand. And on the right-hand side, we have the price effect on the compensated demand minus an income effect. And what we have used here is that we know from Shepard's lemma that this partial can be written as xj. So we have an income effect that is weighted by the amount of good J that is consumed by the consumer. And we have a price effect. So the taken together, the Walrasian price effect can be split up into a compensated price effect and a weighted income effect. Of course, we can also have that I equals J. Then we have the own price effect, but any J different from I is allowed as well. So with n goods, there are n times n Slutsky equations, and we can even build a matrix of all these price effects that would then be the Slutsky matrix. Now, one thing that is interesting and not too intuitive, to be honest, is that the Slutsky matrix is symmetric. That means the compensated price effects are symmetric. So look at this equation. So on the left-hand side, we have the effect of a small price change for good J on the demand for good I. And on the right-hand side, we have a small change in the price of I on the demand for J. And well, what we want to show is that, well, these two sides actually are equal. So how can we show that these two sides are really the same? Well, we can employ Shepard's lemma and rewrite first the left-hand side. Now, from Shepard's lemma, we know that the demand for good I can be expressed as the derivative of the expenditure function with respect to its own price. So let's go down here and rewrite H as exactly that derivative, the derivative of the expenditure function with respect to the its own price. Now, clearly, on the left-hand side, there is another derivative. It is the derivative of compensated demand with respect to the gross price, Pj. So on the right-hand side, we have to take that second derivative as well. So we differentiate the expenditure function twice. First, with respect to Pi to get demand. And secondly, with respect to Pj to get this derivative. So with the help of Shepard's lemma, we've rewritten the left-hand side as this. Now we can do the same with the right-hand side and receive this expression. And then we need to show that actually these two second derivatives of the expenditure function are the same. Now, the only thing that differs between this here and this here is, well, that somehow the sequence of the partial derivatives differs. But this has actually no effect on the value of these cross derivatives, because there is Young's theorem that says for any continuous differentiable function f of a and b, it holds that it doesn't matter in what sequence the derivative takes place. It's always the same value. Therefore, we have that this expression by Young's theorem equals this expression. And this means that this expression here equals this expression. And that is exactly what we claimed up front. We have a symmetry of the Slutsky equation or the compensated price effects of the compensated demand function. These are symmetric. So the last instrument from the toolbox that we need is Roy's identity. So what does it say? So it says that differentiating the indirect utility function with respect to price Pi yields minus xi times the shadow value of income. So it's a simple sentence, but it may be that some concepts of this sentence or included in that sentence are new to you. So you may not know what an indirect utility function is, and you may have difficulties understanding the shadow value of income. We'll come to that in turn. So to understand the indirect utility, look at this function. So V is the maximum attainable utility as a function of prices and income. So the idea is not that the consumer is interested in the prices itself or in the income itself, but because of a budget constraint, lower prices will typically allow to buy more goods, and that will typically yield higher utility. So for that reason, prices and income may show up in such an indirect utility function, which makes sense, not, as I said, because we are interested in prices in themselves, but because they change the budget constraints. And this is why an indirect utility function has prices and income included. Now, if we want to maximize the indirect utility, we have to choose the appropriate consumption bundle. Let's assume that given our price vector, P, and our income Y, X star is that consumption bundle that is optimal in that case. And that the utility that can then be attained is U star. Hence, we can write, at least if we adjust the income appropriately, that The maximum attainable utility is exactly this utility U star. What we have to do to make sure that this equation is right is plug in here the right amount of income. How can we do that? Well, we can take advantage of the concept of the expenditure function, which exactly tells us how much money is necessary at a given price vector so that a certain utility level is attained. So we plug in here the expenditure function. So after equating the actual maximum utility with the indirect utility function using this trick, we can now simply take the partial derivative with respect to, say, the price pi. And then we get two effects when taking this differential. The first is that pi is an element of this vector p. So by changing it, we get an effect on the indirect utility v. That's this first term. And then I have a second effect that works through the effect on the expenditure function. And then the changed expenditure function, which is the change y we plugged in here, that changes v as well. That's an indirect effect, and that's captured by multiplying the inner derivative and the outer derivative. And both effects here have to add up to 0. How come? Well, the left-hand side doesn't change. It's fixed at u star, and therefore the change from the price change is 0. So now we're almost done. The only thing that we need to do is rewriting this equation. We keep this partial on the left-hand side. Then we rename this here and say, well, it is the change in the indirect utility that is induced by a small marginal change in income. So we call that the shadow value of income and denoted by lambda. And this here is the marginal derivative of the expenditure function with respect to the price pi. And we know from Shepard's lemma that this is nothing else than xi. And therefore, we have this equation saying the partial derivative of the indirect utility function with respect to the price of good I equals the amount of xi consumed times minus the shadow value of income. This completes the proof. And this also completes our little excursus into the microeconomic toolbox that we need to have in place so that we understand optimal tax theory.